Hi everyone, welcome to this tutorial on basic VLSI design. I am Goura and today I am going to break down seat resistance of chapter 4 step by step. So grab a pen and let's dive right in. The active devices of most technology having been dealt with some measure, it is now appropriate to consider their interconnection as circuits. The wiring up of circuit takes place through the various conductive layers which are provided by the MOS processing, and it is therefore necessary to be aware of resistive and capacitive characteristics of each layers. The main objective of this chapter is to find seat resistance Rs, standard unit capacitance Cg, and delay unit tau. Consider a uniform slab conducting material of resistivity ρ with W, thickness T, and length between two faces L. So the resistance between two opposite faces RAB is rho L by A, where A is TW. By reforming this equation, we can write L by W into rho by T, where L by W is Z. For feature size, L is equal to W, so Z becomes 1. So RAB is equal to rho by T is equal to RS, where RS is ohm per square or seat resistance. If you notice the seat resistance equation for feature size, which is independent of area of the square. For example, a micrometer per side square slab of material has exactly the same resistance as a 1 cm square slab of the same material if the thickness T is same, when length and width is different. In this case, Z not equal to 1, so RAB is Z into RS. This is the table of typical seat resistance RS of most layers for 5 micrometer, 2 micrometer and 1.2 micrometer technologies. For metal, the seat resistance RS is 0.03 for 5 micrometer technology, 0.04 for 2 micrometer and 1.2 micrometer technology. For diffusion layer, the typical seat resistance RS is 10 to 15 ohm per square for 5 micrometer technologies and 20 to 45 ohm per square for 2 micrometer and 1.2 micrometer technologies. Similarly, for silicide, polysilicon, N transistor channel and P transistor channel, seat resistance RS is given. Now we want to calculate resistance for these transistors and for this transistor. For the transistor 4.2A, the resistance is Z into RS. We can clearly see that L is 2 lambda and W is 2 lambda, so Z is 1 and RS is 10 to the power 4 from the table. So the resistance for this transistor is 1 into 10 to the power 4 ohm per square or 10 kilo ohm. Similarly, the resistance for this transistor is R is equal to Z into RS, where Z is equal to L by W. In this transistor, L is 8 lambda and W is 2 lambda. So Z is L by W, it means 4, and RS is 10 to the power 4 ohm per square from the table. Hence the resistance for this transistor is 4 into 10 to the power 4 ohm per square or 40 kilo ohm. Now if we want to calculate on resistance for NMOS depletion mode inverter, for pull-up network, Z pull-up is given, that is 4. So on resistance is equal to Z into RSN, where RSN is NMOS seat resistance from the table. So R1 is equal to 4 into 10 to the power 4, that becomes 40 kilo ohm. For pull down network, Z pull down is given, that is 1:1. So R1 is equal to 1 into RSN. RSN is the seat resistance for N transistor. So R1 is 1 into 10 to the power 4, that becomes 10 kilo ohm. Now the total on resistance for NMOS depletion mode inverter, that is 40 kilo ohm plus 10 kilo ohm, that is 50 kilo ohm. If you want to calculate on resistance for CMOS inverter, when input is 1, the pull up network is off but pull down network is on. So in this case, we only get the pull down resistance. In this case, Z pull down is given, that is 1:1. So on resistance is 1 into RSN. RSN is seat resistance for N channel transistor. So R1 is 1 into 10 to the power 4, that is 10 kilo ohm. When V input is 0, the pull-up network is on but pull-down network is off. In this case, we only get the resistance for pull-up network. Z pull-up is given, that is 1:1. So R1 is 1 into RSP, where RSP is the seed resistance of p-channel transistor. So R1 is 1 into 2.5 into 10 to the power 4, that is 25 kilo ohm. For CMOS inverter, no static resistance from VDD to VSS, as the ratio rule is not applicable.